let's try a related rates problem that has to do with a volume. So in this case, we're going to use a cone. So again, we're going to kind of use our strategies. We're going to first try and understand the problem, which I like to do as I read it. I like to develop a mathematical model of the problem, mainly through drawing it with pictures and making sure I understand what is constant and what is variable. Once I do that, I'm going to write an equation relating the variable whose rate of change I seek with the variable whose rate of change I know, with the variables. Once I get that, I can differentiate both sides of the equation, substitute in my values, and then I'm going to have an answer. So let's kind of look at this problem. A conical paper cup is 20 centimeters tall with a radius of 10 centimeters. So I don't know if you've ever seen these kind of conical cups, but they look just like a cone. You put your hand around it and you drink it. So I know that the conical cup is 20 centimeters high, and I also know that the radius is 10 centimeters. That's of the whole giant cup. Now it is being filled with water. Let's actually make the water blue. Wouldn't that be nice? So it's being filled with water so that the water level rises at a rate of 2 centimeters per second. So this is the water level right here. That's how high the water is. So I know that that is changing at 2 cm per second. At what rate is water being poured into the cup? So water is kind of going into this cup here, when the water level is 9 centimeters. So right here, this distance right here, from there to there, is 9 centimeters. So water is being poured into the cup. That means this is a measure of volume. While pouring water into the cup is filling up, and I want to know at what rate the water is filling up. Okay, so what do I seek? At what rate is water being poured into the cup? I am seeking dV to dt. I'm seeking the rate of change of volume, how much water I am pouring into the cup over time. What do I know? Well, I know a few things here. I know, let's call this, this 9 centimeters, let's call it h, because that's the height of the water. So we know that h is equal to 9, but that's a changing figure. That's not static, that's a changing figure. And what else do I know? Well, I know that dH to dt is equal to 2, because they gave me that information right here, that the water level is rising at a rate of 2 centimeters per second. Well, at this point, I think that's all that I know. So I'm going to see if I can figure out a formula here. So I know that volume of a cone is equal to 1/3 pi r squared h. And I can see right now that I have a little bit of a problem, because I am seeking v. I know I'm seeking v. I know h. I don't know anything about r yet. So let's kind of go back and look at our picture and see if we know anything about r. Well, in fact, I think we do know a little bit about r. One thing we know about r is that, well, this cone, if I kind of looked at it like straight on, you can kind of see that I have a triangle. And I know that this height of this triangle is 20. And I know that the radius is 10. So anywhere that I draw a line, like representing the height of the water, the ratio between the radius and the height is going to be the same as the larger cone. So I know that my radius is equal to, well, my height divided by 2. Let's just look at that a little bit more. Let's look at it as a proportion. I know that the height of the cone in relationship to the radius of the cone is 20 to 10. And I know that that's going to be true for any height of water in the cone to its respective radius in the cone. So I know that any height to radius is going to be 2 to 1, which is the same thing as saying, well, I can cross multiply here. So 2r equals h. So r is equal to h divided by 2, which is what we wrote right there. But I kind of walked you through the steps to be able to see that. So this is a little bit more of a complicated problem because I have to be able to look for different kinds of similarities in the different forms that I'm using. So I know that r is equal to h over 2. Delete that so I have a little bit more room. Get rid of this one too. And I'm working with this formula right here. So I still don't know what dr is. And so if I differentiated this, I wouldn't really know what to do because I'd end up with a dr. But since I know that r is equal to h over 2, I can change this formula into volume is equal to 1/3 pi h over 2 squared times h. All I did was substitute h over 2 for r. So now let's see if I can't simplify this a little bit. I get volume equals 1/3 pi, and this would be h squared over 4 times h. Well, let's just make it look a little bit different. So volume is equal to 1/3 pi times 1/4 h squared times h. Well, I can multiply the 1/3 and the 1/4, and I can multiply the h squared times the h. So I get volume is equal to 1/12 pi h cubed. So now I have a mathematical model that relates the variable that I am seeking, the rate of change for the variable I am seeking, to the variable that I know, which is h. So let's kind of take the derivative of both sides and see what happens. The derivative with respect to time of v, and the derivative with respect to time of this entire equation right here. So what I am seeking here is dv to dt, and that is equal, I have 1/12 pi, that's a constant. I can pull that through. So let's just call it pi over 12 d dt of h cubed. So that is equal to pi over 12, well, that would be 3h squared. Now remember, h is a function here. H is something that is changing with respect to time. So I did the outside, now I got to do the inside, dh dt. So I have my dv dt is equal to pi over 12, 3h squared dh dt. And now I can plug in some numbers. Well, I'm seeking this. I'm seeking dv dt. But at this particular moment, I have pi over 12, 3. Now my h is 9, so I have 9 squared times, well, dh dt, what was that they gave me? 2 centimeters per second. dh dt times 2. So I have pi over 12 times 3 times 81 times 2. Well, what can I see here? I can see that 3 times 2 is 6, and that would make this 12 a 2, right? A 6 in the numerator, a 12 in the denominator. So I have pi times 81 over 2, and if we write that a little bit nicer, it becomes 81 pi over 2. Now I got to go back and look at the 81 pi over 2, what? Well, I'm looking for volume, and I'm measuring this in centimeters per second. Volume is a cubic measurement, so this is centimeters cubed per second. That is the volume that is being poured into this, this conical cup. Now that is the correct answer, but I'm going to show you something really interesting that one of my students here in 2017-18, the graduating class of 2018, Jeanine Hernandez, she took a little bit of a different tack on this problem, which I have to say is a little bit easier than what I did. So Jeanine got to this same spot right here. She had what we see, and she had what we know, and she got to the same spot here, volume equals 1/3 pi r squared h. And as you can see, what we did was we substituted h over 2 for r and did a whole bunch of arithmetic here to kind of calculate that. But I'm going to erase all that stuff, because I'm going to show you what she did, which I thought was extraordinarily clever and turned out to be easier. So Jeanine looked at this formula and she said, well, you know, I can see very clearly that when I take the derivative here, I'm going to have dv to dt, which is what I'm seeking. And I'm also going to end up with a dr dt as well as a dh dt. But I don't know what dr dt is, she says. Well, I want to find dr dt. In fact, let's do it a little bit differently here. Let's actually differentiate this whole thing so you can kind of see what we're looking at. So she took the formula and she said, okay, I have dv to dt is equal to, well, if I take the derivative with respect to time of 1/3 pi r squared h, well, we know we can take the 1/3 pi and pull that through the derivative, so that's going to equal 1/3 pi d to dt of r squared h. Well, now I have to take the derivative of this. I have a product going on here, so don't mess up. I have a product which is r squared times h, so I got to use the product rule, uv plus uv prime prime. But that's not really too hard, because that's going to be 1/3 pi. Now, the derivative of r squared is going to be 2r dr dt, because r is a changing variable. It's changing with time, so I have to do the outside and the inside, times h, plus, well, u, which is r squared, times, well, the derivative of v, which is h, is just dh dt. Well, now I can just plug in some numbers. So I have dv to dt is equal to 1/3 pi, and I have 2, now my radius is 4.5. My dr dt was simply 1. And my h was 9, plus r squared, remember r is 4.5, so 4.5 squared, dh dt is 2. So let's see what we get. I get 1/3 pi times this is 9 times 9, which is 81, plus 4.5 squared. I'm going to have to do this in decimals, I think. So I got 4.5 squared. That's going to be 20.25 times 2. So I have 1/3 pi times 81 plus 40.5. Well, I think we're just going to work this out. We're going to go parentheses 1 divided by 3 close parentheses pi times parentheses 81 plus 40.5 close parentheses, and I get 127.235. Well, let's see something here. 81 pi divided by 2. What do you know? It's the exact same number. So, a slightly different approach. I really liked the way that that Jeanine used this very simple r equals 1/2 h to be able to derive dr dt. It works out. It turns out that became very helpful in many other problems. It doesn't have to be a really complicated formula to relate the two variables. Just any formula that relates the two variables, as long as I can relate a variable whose rate of change I seek, which was dr dt, with a variable whose rate of change I know, which was dh dt.